In this video, I will introduce the Riemann sum, which is basically estimating the area under a curve by making small rectangles and finding the area of each rectangle and then adding them up. I'll go over the different techniques of estimating area under a curve, such as right, left, midpoint, and trapezoidal method of Riemann sum. Okay, so this is part one of Riemann sum. So let's first talk about what is antidifferentiation. It's basically a function of f is called an antiderivative of f prime of x equals f of x. So it's also the process for taking a derivative and finding the original function. It's also antidifferentiation. Antidifferentiation is the same as finding the indefinite integral. So basically, it's just the area under a curve. That's what antidifferentiation is. So what is integration technique used to find an indefinite and definite integral? So what is an indefinite integral? Indefinite integral. It's basically a family function whose derivative is f of x, and an indefinite integral has no limit values. So in an indefinite integral, later on in calculus, you'll notice that each answer has a plus c. That c represents a constant. Okay. So let me show briefly. So let's talk about, let me show you an example. Let's say we had two linear lines. Let's call this linear line y equals x plus 2, and the other one y equals x. So did you know that when you take the derivative of each line, the derivative of y equals x plus 2, we'll call it, the slope of that would be 1. And then the derivative of m is also 1. So basically, you get the same slope, right? You're finding a family of functions, right? So if you take, here's, for example, f of x equals x minus 3, take the derivative is 1. The derivative f of x equals x plus 2, and if you take the derivative of that, it's also 1, etc., right? They all have a slope of 1. So what is a definite integral? So now with a definite integral, it basically finds a number that represents the area under a curve from A to B. So definite integrals have limit values. So in a definite integral, you're no longer going to have a plus c. You will have a final answer, like an exact value. So in a definite integral, you have boundaries, lower boundary A and upper boundary B. And then you take the integral. So if you take the area under those boundaries, you're going to get an exact value. Okay. So in an indefinite integral, we are finding a numerical value, not a family function. So yeah, what is integration used for? So why do we do this? Is because we do it. We can express it in the real world. We can use it in the real world. So you can integration can be used for finding position, distance, length, velocity, acceleration, speed. You can also use integration to find area, volume, surface area. And you can also find it to find prediction and probability. In the science world, you can find it to find work, force, center of mass. So how did integration come to be? So it started with the area problem or the distance traveled problem. Integral is Greek for whole. So when when we integrate, we put parts or elements together to make a whole. So how can you approximate the area under the curve? So what is, yeah, this is a good question. Why do we have to approximate versus finding exact value? That's a good question. If it were up to me, I would never approximate. I would want the exact value. So so what's the different? Yeah, so when you're approximating, you're going to use the Riemann sum, right? And then later on in calculus, you can find the exact values between two boundaries using the integration rules. So so if you look at this example, how can we approximate the area under the curve of f of x equals x squared plus 4 from the boundary 0 to 2? So what you do is make rectangles, right? So let's say I made one big rectangle from um, 0 to 2. So here's the x value 0 and 2. So if I make this like one rectangle like that, uh, it's too much. It's not accurate, right? You have this space right here that isn't part of under our curve, right? We only want this area, right? So what you could do is make more rectangles. So if I make two rectangles like this, is this more accurate? A little bit more, but not too much. So it's still too much if you make two rectangles, so you make more. So so here, so the distance from 0 to 1/2, the distance halfway point would be like 1/2. And the distance from 1 to 2, the distance halfway point would be 3/2. So if you make a rectangle from here, so wait, if I make a third rectangle from 3/2, uh, still not good enough. So what you want to do is make as many rectangles as possible to get a more precise area, right? So yeah, let me say that again. You want to make as many more rectangles as possible to get a more precise area or a more accurate area. So let me write that down. So more rectangles. And when I say more, you can go to infinity. And that's when we're going to have to use that sigma notation because we're dealing with infinities, right? Right. More rectangle. Okay, so let's see. If I made one more here, and then I made some more here, and then I made one more here, it's getting more accurate, right? Oops. And then you can make more and more, right? And more. So then what we're going to next is talk about the different methods of estimating under a curve. So that's like, yeah, so Riemann is basically approximating area under a curve. Okay, so yeah, you keep dividing to create more rectangles. More rectangles is good. So let's look at these. Let's look at a rectangle. So let's say we had this curve from A to B, right? We stop at the point B and we start at A, right? So we got to find the area of a rectangle. So what is the area of a rectangle? Is base times height or length times height, right? So the base is what we call the change this distance here, the delta x. So the base is going to be delta x. And then the height is so whatever your x value is, plug it into your function. So the height would be f of a, right? Height is an actual number. So, I mean, unless you know, so they'll give you a function. They don't give you a function for this one, but let's say f of x equals x squared plus, I don't know, 1. And then, well, let's say a value is 1. So to find the height, you just plug in 1 to the function, which is 2. Okay, so that's how you find the height. And yeah, so you can write this as a sigma notation because we can have infinity rectangles, right? So you could say f of x equals the limit of delta x as x approaches infinity, and you get this. I equals a, stop at the point B, and then f of xi, this is our height, and then your width is the delta x. Okay, so it can be expressed as integrals from a to b. This is bounded boundaries of f of x, and you'll learn this later on in calculus. They'll get very sophisticated rules. It's actually kind of fun. So what we want to do is we want to change x so that to be so little. So we want to change the change of x to be so little so we can calculate infinite of rectangles. So we want the change of x so little so we can calculate infinite of rectangles. Okay, so we have a rectangle, right? Your base is the b, the height is h. You can also say the base is the delta x and the height is f of x, right? And oh, I just rewrote it here again, which somehow converts to this. Okay, so we're basically estimating to think what would happen. Okay, so let's talk about, so now we know that estimating is involved with Riemann sum. Now let's talk about the different methods we can use. So you can do the left endpoint. So you could do left hand, right hand, midpoint, and trapezoid. Okay, so let's say we had a curve like this. I kind of did this one. And how do you do the left hand point? So what you want to do is, here, let's use red. So I kind of did this one on the own. So here's, so imagine this image without this rectangles. So just with the curve. And we're going from 0 to 2. And what else? We know that 1 is halfway point, and then you have 1/2 here, 3/2. So the total distance, horizontal distance, is a constant of 1/2. So we have a width of 1/2. So that's constant. So this distance 1/2, this is 1/2, this is 1/2, 1/2, etc. Now, if you want to do the left-hand point, what you do is put start on the very left, make a straight line. So I'm starting at 0, making a straight line. And then what you want to do is from go across and then go down again. Okay? And then go across. Oh, no, I'm going wrong. Okay, so what you want to do is I made the so you're starting on the left hand side. I made it up. I mean, I didn't make it up. I did it wrong. I was going right. So what you want to do, so for example, at 1/2, draw your rectangle, and then you're going to go to the left like this. So that's how I made this rectangle. And then at 1, right, make a straight vertical line and then go to the left. And then that's how I got this rectangle. And then from 3/2, make a straight line from the curve. And then if I go to the left, it makes this rectangle. So as you can see, you have this little space that's not part of, that should be included, but it's not because it's the left end point. And then again here, and then go from left. And that's how I made this rectangle. So is left end point the most accurate? No, because you have this area that we need to calculate, which is not part of it. And then we have this space that's still not calculated. So you do have a width of 1/2. Yeah, and probably not the most accurate, but basically you just start on the left hand, and so you start here from 1/2 and then go to left. Now let's talk about this. So imagine the same curve but doing the right hand point. So instead of using the left hand point, you go to the right and slide over. So what I mean is like you start at 0, put a straight line, right? And then go to the right. And then at 1/2, go put a straight line and go to the right. Straight line, go to the right. Straight line, and then go to the right. And as you can see in the right hand side, we're probably overestimating because we don't need this curve, right? We don't need this area. We don't need this area, and we don't need this area. So yeah, it's a little bit of an overestimate. Okay, so that's how you do right hand. And as you can see, the width is still exactly 1/2. Okay, number 3, midpoint. So the midpoint, it gets a little bit more accurate. So midpoint and trapezoid method are probably the most accurate. So as you can see, we have we have a new length. So we have 1/4, 3/4, 5/4, and 7/4. How do I get those values? So what you do is take the average. So from 0 to 1/2, what is the average? You just add 0 plus 1/2 divided by 2, you get 1/4. So you make a straight line at 1/4, and then you're going to draw this two different rectangles, right? And then the same thing with, so what's a halfway point? What is the halfway point between 1/2 and 1? So you just take the average of 1/2 and 1, and you get 3/4. So that's how I got this vertical line. And then the distance between halfway point between 1 and 3/2 is 5/4. And then the halfway point between 3/2 and 2 is 7/4. Okay, so I have uh, more rectangles, and it's really more accurate because it's really more under the curve. It's not above or below. It's just right. Now, what about trapezoid? So trapezoid is the most accurate method. So yeah, as you can see, one rectangle like this is a trapezoid, and basically what you do is, uh, so what you do is you take both height, create a trapezoid and approximation, go straight up from both left to right, and then connect to make a trapezoid. So here's 1/2 curve, because a curve is like that little trapezoid. So you have this rectangle, and then here's that 1, right? Make a straight line. And instead of making like a go across, you make a curve because a curve is related to a trapezoid, right? Same thing with 3/2. Here's 3/2, curve, and you get this area, this rectangle. And then at 2, curve, and then you got that rectangle. So this is a trapezoid. So just imagine that this rectangle right here rotated, and you have this trapezoid. So the height is delta x, and then, yeah. I mean, the width is delta x, and the height is f of x of whatever, right? Whatever your x value is. Yep, so you go straight up from both left to right, and then connect it to make a trapezoid. So that's exactly what he did. So here's 1/2. Make a little curve to create a trapezoid, and then go down. Here's that one curve, and then go down. 3/2, make a little curve and go down. And 2, curve and go down. Okay, blah, blah, blah. Okay, so we did that. And we know that the area of a trapezoid is you add up both bases, b1, b2, times it by the height and divided by 2. So you can also express it like this. Okay, now imagine using the same method, but using a decreasing curve. So here we have a same method, decreasing curve, and then you do the left-hand point. So so you start at 0, and then wait. So here's the. Let's pretend this is your curve, the red one. Whoops, right here, right? It's a decreasing curve, and if you do the left-hand point, your rectangle is above here. So you start at 0, right? Draw a straight line, and then you go left, and then go down. Same thing with 1/2, go left, go down, left, go down, and then left, go down. Okay, so that's the left-hand point. As you can see, for a left-hand point for a decreasing function are above the curve. So if it's a decreasing function like what we have, the rectangles are above the curve. What about if it was a decreasing function and you had to do it using the right-hand point? So if I start at 1/2, right? Here's the curve. Here, let's make the curve red. Put a straight line like this. And then go on the right-hand side. So you're going to go to the right and go down. Same thing with 1, put a straight line like that. And then go to the left. And then 3/2 is like this. Go to the this. And then at 2, and right to the left. Okay. Shoot. Here, let me do it again. I always get this mixed up. So left-hand point. So what you do is you start at 0, right? No, you start at 1/2, right? And then you go left. So you start at 1/2, and then you go left. So that's why it's above the curve. And then you start at 1, and then you go left. So you have this triangle, and then the rectangle, start at right, 3/2, and then you go left. And then you start at 2, go left. So as you can see, it's still it's above the curve. And then on the right-hand side, so you start at 0, and then you make your way to the right to 1/2. So that's how I got this rectangle right here. And then go from 1/2, go right, and then from 1 go right, and then 3/2 go to the right. So as you can see, it's below the curve. And if you do the midpoint, so just like here's 1/2. From 0 to 1/2, the halfway point is 1/4 because you just take the average between 0 and 1/2. Uh, from 1/2 to 1, the halfway point is 3/4. And then from 1 to 3/2, the halfway point is 5/4. And then from 3/2 to 2, the halfway point is 7/4. And then you have the trapezoid. So here's 1/2, and then make a little trapezoid. So you have to go around this curve. I mean, exactly on this curve, and then it creates a trapezoid. And same thing with 1, do the curve thing, and then 3/2 curve, and then 2. So as you can see, the trapezoid is probably the most accurate. So basically, the more accurate is, the better the answer. Midpoint trapezoid is probably the most accurate area of the values. Left and right are great rounding estimation. So so what you want to do, let's compare our answers with an increasing curve and a decreasing curve. So if you look at your choices, if you look at your drawings, right, between an increasing curve and a decreasing curve, what can you conclude about the rectangles? So basically, if f of x is an increasing function, right? So an increasing function was like the one we did, like this, right? That's an increasing function. Um, so it says if f of x is an increasing function, then the left Riemann sum is an underestimation. But let's go back to our image. Is that true? An increasing function, and then look at the left endpoint. Here's your increasing function, left-hand point. Is that true? Is an increasing function of the left endpoint an underestimation? Yes, because we have not collected the area from here, right? So that is definitely true. What else can we say about what else can we say? We can also say and the right endpoint is an overestimation. So look at your increasing function and look at the right endpoint and tell me, is that going to be an overestimation? Here's an increasing and right endpoint. Yes, we don't need the area of this, so this is too much. So yes. So the other statement says if f of x is decreasing, so if f of x is a decreasing function, then the left Riemann sum is an overestimation. So is that true? So go to your decreasing curve. This is an increasing. So decreasing is here's your decreasing. So if f of x is a decreasing function, then the left Riemann sum is an overestimation. So here's a left. Is it an overestimation? Yes, because we don't need the area of these stuff, right? Too much. And then on the right, Riemann sum is an underestimation. So here's a decreasing, here's a right method, right endpoint method. And is that really an underestimation? Yes, right? Because we need the area of this and this, and this, which we don't have. So it is definitely an underestimation. Yeah. Yeah, so now I just kind of introduced you to the left, right, midpoint, and trapezoid method of estimating a Riemann sum. In the next video, we'll do some problems. So I'm going to stop right here.